In this video, we will be using the EFI Memory Map to find out what sections of memory we have available for our kernel to use. The GitHub link will be in the description if anyone would like to follow along. Let's get started. Alright, so the first thing we need to do is get the EFI Memory Map and pass that to our kernel so the kernel knows about all the memory sections that we have to work with. So we need to go back into our bootloader code. And somewhere near the bottom, we need to get the memory map. And to do that, we need to start by declaring a few variables. So we need the EFI Memory Descriptor pointer map equals null. We need a uint n map size and map key. And we need uint n descriptor size. So these four variables here, I'll explain what they do. The EFI memory descriptor is just a pointer to the memory descriptor struct. And this memory descriptor struct contains things like the number of pages of the memory section, the physical address of the memory section, and the type of the memory section. The map size is just the complete size of the map in bytes. The map key is just something that we need in UEFI, the kernel doesn't need it. And the descriptor size is how big each one of these descriptor entries is. Alright, we need one more variable, uint n32 descriptor version. And this is just the version of the descriptor struct that we're using. This also doesn't matter and we won't be handing it over to the kernel. Alright, now to actually get the memory map, we can do some curly brackets for clarity. So the first thing we need to do is use the getMemoryMap function to get the size of the map so that we can allocate some memory for it and then get the actual map. So we need to do system table BootServices getMemoryMap. And we need to hand it a few parameters, so we need the reference to map size, the map, the reference to map key, reference to descriptor size, and a reference to descriptor version. Alright, so that will give us the map size, the map key, etc. Now we need to allocate some memory to hold the map. So we'll do system table. We'll just copy this line here. So system table boot services allocate pool EFI loader data map size void pointer reference to map. And now we can just call the getMemoryMap function once again. Alright, so now we should have the memory map in the UEFI memory. We need to hand it to the kernel. And to do that, we need to modify our kernel start function pointer. I'm just going to move this down a little bit to above where we call it, just to make it a bit neater. Alright, so instead of just piling more parameters on here as we hand more things to the kernel, I'm going to create a BootInfo struct. So I'll go up above the EFI main function, and I'll do typedef struct BootInfo. And inside the BootInfo will contain everything that we've been handing to the kernel. So we need the frame buffer, pointer frame buffer. We need the PSF1 font, pointer PSF1 font. And now we need the memory map as well. So we need a EFI memory descriptor pointer. We need the map size and we need the descriptor size. So we need the EFI memory descriptor mmap. I'll just rename PSF1 to keep with naming conventions. Even though my naming conventions have been all over the place, I'm trying my best. And we need a uint n mmap size. And we need a uint n mmap descriptor size. Right. Now we can create a BootInfo struct. So BootInfo's frame buffer equals new buffer, BootInfo's PSF1 font equals new font, BootInfo's memory map equals map, BootInfo's memory map size equals map size, BootInfo's memory map descriptor size equals descriptor size. Alright, now we can get rid of this frame buffer pointer and PSF1 font pointer and replace it with a BootInfo pointer. And the same with over here as well. Now, instead of giving our kernel start function new buffer and new font, we can just give it a reference to BootInfo. Right, now that we have the memory map, we can also use that to exit boot services. We'll do that just before we call the kernel start function. Now, it's important to call exit boot services so that 1, the EFI runtime doesn't cancel our bootloader after 5 minutes, and also terminating our kernel after 5 minutes because of the watchdog timer, thinking that our EFI application has stalled. However, it hasn't. Another thing is that we need access to a lot of system resources that the UEFI runtime is currently using. We need to exit boot services so that we can use those resources. So we'll do system table boot services exit boot services, and we need to give it the image handle and the map key. And that's what we defined the map key for, so we could exit boot services. Alright, so I do have an error. uint n32 should be uint32. Alright, now that we've done that, we just need to edit the kernel to take this BootInfo struct instead of the other parameters, because as it is now, it's not going to work. So we'll copy our BootInfo struct and then jump over to our kernel source and just paste that in there anywhere, just above the start function. We'll change this into a C++ struct. There's a couple of things that our kernel doesn't know what it is yet, just such as EFI Memory Descriptor and uint_n. So uint_n is just it's the native int size. So on a 64-bit system, it's 64 bits, and on a 32-bit system, it's 32 bits. So on our system, it will be a uint64t. Same with the map descriptor size. And the EFI memory descriptor, we haven't declared that yet, we haven't defined it, so we'll just change it into a void pointer. Now before I forget, I had an error here, I had to put that quotation mark. We need to change these variables from using this frame buffer and PSF1 font into a pointer to this BootInfo. So we'll do a BootInfo pointer, BootInfo. And now every reference we had to frame buffer and PSF1 font must go through the BootInfo. Alright, that should be it. Now we should be able to compile the kernel, and it compiled correctly, and we can do make build image. Now as you can see, it's working just as it was before, printing our text to the top left of the screen. So now that we have the memory map available in the kernel, we can use it to do some memory functions. Alright, break check my friends. Make sure you take a second to stand up and have a stretch. Alright, now let's get back into it. To make sure we can actually access the members of the EFI memory descriptor in a meaningful way, we should define a struct for it. So, to get started, we will create a new file and we'll call it EFIMemory.h, add in our pragma once, and from kernel.cpp we can include EFIMemory.h. Inside of EFI memory we can declare our struct, so our struct is EFI memory descriptor, and we have 5 members that we need to put in here. So the first one is a uint32t, which we need to include standard int to use. So we have uint32t type, so that's the type of the memory section, be it EFI conventional memory or ACPI reclaimable memory. We have a void pointer to the physical address that this section of memory is at, And we have a void pointer to the virtual address that this memory is mapped to. Then we have a uint64 of the number of pages. So this number times 4096 is the amount of bytes that this memory section spans. And we also need a uint64 attribs, which is just the attributes, which is extra information that the memory descriptor might contain. Right. Now that we have that, we can go ahead and declare some type names, like some strings for the different types of memory descriptor sections that we have. So we'll do an extern const char pointer EFI underscore memory underscore type underscore strings. And this is an array. Right, and then we need to create EFI memory.cpp, and inside of EFI memory.cpp we need to include EFI memory.h. And now we need to define our strings. So we'll do a constant char pointer EFI memory type strings, array, curly brackets, and a semicolon at the end. Now I just need to give a shout out to RizXT for giving me the solution to this, because the source that I had gave me the wrong EFI memory type strings. So shout out to RizXT for giving me the correct memory type strings. I'll leave a link to their YouTube channel in the description if you'd like to check it out. So we have 14 memory type strings that we need to define. So the first one is EFI reserved memory type. Then we have EFI loader code. Then we have EFI loader data. Then EFI boot services code. EFI boot services data. EFI runtime services code. EFI runtime services data. EFI conventional memory. EFI unusable memory. EFI ACPI reclaim memory. EFI ACPI memory NVS. EFI memory mapped IO. EFI memory mapped IO port space. EFI PAL code. Right, so I won't go into what all of these different types are, but I will cover a couple of them, and those ones are EFI conventional memory. So EFI conventional memory is just a memory section that UEFI has not used. So that is memory that we are free to use inside of the kernel. Unusable memory is pretty self-explanatory. And ACPI reclaim or reclaimable memory is memory that we can use, but only after we have gotten the information that we need from the ACPI tables. We can use a couple more of these memory types, but for the purpose of this tutorial, we will only be using conventional memory and maybe eventually the ACPI reclaimable memory, because as far as memory space goes, that is pretty much all we'll need, because EFI conventional memory is pretty much 98% of total system memory in most cases. Alright, now we can test if our EFI memory map has been handed to the kernel correctly by printing out its data to the screen. So we'll get rid of all of this rendering information. We'll keep the new renderer cursor position equals whatever, but we'll change it to new renderer dot cursor position dot y plus 16. So we're doing new renderer.cursor position equals 0 on the x and the current cursor position y plus 16. So it's just going to the next line. Right, now we can go through each of the memory map entries and print their details. So The first thing we need to do is find out how many memory map entries we actually have. So that's pretty simple. That's uint64 memory map entries equals memory map size divided by memory map descriptor size. Right, and I need to explain something. We can't just use size of EFI memory descriptor. We can't use this because UEFI actually gives a different descriptor size depending on the implementation. So you can't have a fixed memory descriptor size because this is dynamic. So you need to use the size that's given to us by UEFI. Right, so we can make a loop for int I equals 0, I less than memory map entries, I++. Now we need to get a EFI memory descriptor pointer to our current descriptor. So EFI memory descriptor pointer descriptor equals casted to an EFI memory descriptor pointer, 2 brackets, uint64t memory map. So we're casting the memory map address to our uint64 so we can do some maths on it without it doing any weird pointer maths. And we'll do plus I times memory map descriptor size. Now I must add that I forgot to do our BootInfo memory map size and so on and so forth. So we just need to put our BootInfo in there as well. Right, so now we have our pointer to our descriptor, we can print the descriptor information. So we'll take our new renderer cursor position equals such and such, so that's our new line function. And we'll do new renderer dot print EFI memory type strings indexed by descriptor type. So we'll go on a new line and we'll print the type for each of the memory sections that we have. Alright, now we can compile that and see what we get. Alright, so we have EFI memory type strings was not declared. And that's because we need a semicolon after EFI memory descriptor in EFI memory.h. Alright, so we've made the kernel. Now we need to make the image. Now as you can see, we are printing all of the memory sections, all of the memory entries to the screen. So we've got boot services code, loaded data, a heap of conventional memory, and so on and so forth. Lots of boot services data and code. That's a lot in QEMU, but on real hardware, it's actually a lot less sections that we have to deal with. I don't know why QEMU has so many sections, but it does. But knowing all of these details without knowing how big each memory section is, isn't very useful. So we'll print how big this memory section is. So we'll go back to kernel.cpp, and on the same line, we can change the new renderer .color to something like 0xFF00FF, just to differentiate the size of the memory as opposed to the memory type. Now we can print a space. Then we can print to string descriptor number of pages times 4096, so that'll give us the amount of bytes, and just to make it easier to read, we'll divide it by 1024, which will give us the amount of kilobytes. Now after that, we can print a space and then KB, and then we can set the color back to white. So now as you can see, we are printing the amount of kilobytes of each memory section just after the memory type. So at the top left, you can see that the fourth block of EFI conventional memory is 174,000 kilobytes. And since we've given QEMU 256 megabytes to work with, that EFI conventional memory is taking up 174 megabytes of that memory. So that's quite a lot. And you can see that there is more sections of EFI conventional memory. So adding all those up, we come very close to the amount of total system memory that we're using in the system. So it's not really very important to reclaim other memory sections unless you're really pedantic about getting those extra few megabytes of memory back. Alright, that will be it for this video. I've been trying to make it a little bit shorter, like half the length of my other videos, so that I can make more videos per week. In the next video, we'll be using the information from the memory map to create a page frame allocator so that we can start allocating page frames for our kernel and eventually user space processes. As always, thank you for watching, and I will see you next time.